as yesterday, we're doing similar things. Today we're going to talk about what's called a biconditional and our definition. So yesterday we talked about conditionals. So if you remember a conditional, it was an if-then statement. So an example of a conditional, I could say, if you are a sophomore, then you will graduate in 2024. Sorry. Okay. If you're a sophomore, then you will graduate in 2024. We talked about the converse, the inverse, the contrapositive, all of those things. Today we're going to talk about what's called a biconditional. Okay? What a biconditional is, it takes your conditional and the converse. So if you remember, the converse from yesterday is where you swap the hypothesis and the conclusion. So my example where I say if you are a sophomore, then you will graduate in 2024. The converse would be if you graduate in 2024, then you are a sophomore. Okay? If both of those statements are true, you can write what's called a biconditional. So bi means two, okay? But it's not two conditionals. It's taking two conditionals and combining them into one. Okay? So how you do this is you combine the two statements together with the words if and only if. So the biconditional for that example would be, you are sophomores if, and only if, you graduate in 2024. Okay? Now you can only write a biconditional if both the conditional and the converse are true. Okay? So let's look at an example of our conditional, the converse, and see if we can write a biconditional here. So my example says, if two segments have the same length, then they are congruent. Well, that's true, right? Two segments have the same length. They're congruent. I mean, that's kind of what it means to be congruent, right? Okay? So if I want to write the converse, remember the converse, you just swap the hypothesis and the conclusion. So we're going to take the congruent, put that first, and then the same length and put that at the end. So it would read something like this. If two segments are congruent, then they have the same length. If two segments are congruent, then they have the same length. Now, if you can write that as a biconditional, that also has to be true. Well, if two segments are congruent, will they always have the same length? That's kind of what congruent means, right? So yes, it's true. So to write the biconditional, okay, you might have to reword it just a little bit, because with the biconditional, you don't need the if-then, okay? You need the two statements, okay? The two segments are congruent, they are the same length, and you're going to combine them together with the words if and only if, okay? For consistency purposes, technically, because it goes both directions, so it's called a biconditional, okay? It doesn't really matter which statement you put first, but for consistency purposes, let's go to the to the original conditional and let's write it in that direction. Now, if you decided to swap them, it means the same thing. It's not that big of a deal. I'm going to grade your homework tomorrow, just so we all do this for consistency. We'll go back to the conditional. So how we're going to write this is we're going to say two segments have the same length if and only if they are congruent. Two segments have the same length if and only if they have the same length. Now going back here to that last little bullet, we talked about the symbols yesterday. So the symbols for your conditional is if P then Q. So P, arrow, Q. If I do the converse, it would be Q then P. For the biconditional, if it is a true biconditional, you're going to read this. P, and then it's going to have an arrow with both ends on it, and then the Q, and you read it P, if, and only if Q. Okay, that's what this symbol, that's the biconditional, looks at. Okay? Now, where the biconditionals are going to come in really handy. all too soon here, we're going to start talking about proofs and things like that. And we're going to be using a lot of definitions. And maybe not in the sense of definitions that you're used to thinking about, like the ones that you look in the back of the book, at the glossary, and copy them down at the beginning of the chapter. But as far as a mathematical definition goes, if something is truly a good definition, a good acceptable definition, three things have to be true, okay? One, it has to use clearly understood terms. Okay, so like up here, two segments have the same length, they are congruent. We've been in geometry for 3-4 weeks now. We understand those words, okay? Clearly defined terms, or they understood their common terms. If you use some crazy scientific term that not the common person is going to know, that's not a good definition. If you have to look up a word in the definition, it's not a good definition, okay? It needs to be precise, okay? So I didn't say, like, if two segments have almost the same length. No, I said if they have the same length. It's very precise. So avoid the words large, sort of, almost, close to, a few. Very precise, okay? But lastly, this is the big thing that we're going to see today, okay? It needs to be reversible. So what we just did by writing the converse, it should be true both directions. If it's true both directions, then we consider it a good definition, okay? Questions on any of that? Okay, this is getting glued into page 23. Page 23 of your notebook. We'll fill out our table of contents. This is 2.3. Biconditionals and definitions. Biconditionals and definitions. All right, so we're going to be given a conditional. They're saying it's true. We want to write the converse. If the converse is true, then we're going to write this statement as a biconditional. Okay, it has to be true. Both the conditional and the converse have to be true for you to write it as a biconditional. So number one, if the sum of two angles is 90 degrees, then the angles are complementary. If the sum of two angles is 90 degrees, then the angles are complementary. Okay, so they tell me that this is true, which the sum of two angles is 90. Yeah, they're complementary, right? The C, it means that they are 90. So, what we first need to do is we need to write the converse. If you remember the converse, you're just going to swap what comes at the end. You're going to put it at the beginning. You're going to swap the conclusion and the hypothesis. So I need to write the complementary first part. The complementary part first, and then the sum is 90 second. So it looks something like this. If two angles are complementary, then their sum is 90 degrees. Now, as we saw yesterday, you could have a conditional that's true and the converse is false. So you cannot write a biconditional unless both of these are true. We know the conditional is true, but if you have two angles that are complementary, and we just write complementary, is the sum of their angles going to be 90? That's exactly what complementary means, right? So I can write it as a biconditional. Now, like I said, you can write whichever part of the statement first. It doesn't matter. It means the same thing, but for consistency purposes, I'm going to go back to the original conditional and go in this order. Don't have to. I'm just telling you that's what the answer he's going to say tomorrow. But you may have to kind of reword it a little bit, okay? But in general, you're going to take the if and the in out, okay? What this is going to say is I need to start with the two angles, okay? I've got two angles. So two angles have a sum of 90 degrees. Two angles have a sum of 90 degrees if, and only if, they are complementary. Two angles have a sum of 90 degrees if and only if they are complementary. So sometimes you might have to kind of talk through it because you do have to kind of rearrange the words a little bit. Okay? All right, number 2. Let's try another one of those. Okay, number 2 says, if two numbers are both even, then their sum is even. If two numbers are both even, then their sum is even. Okay, now we know it's true because they told me it's true, but I mean it is true. 2 even numbers, 2 plus 4, 4 plus, yeah, but it's going to be even every time, okay? Now, before we can write it as a biconditional, we need to check if I'm able to write it as a biconditional, so I need the converse. What would the converse read for this one? Okay, if the sum of two numbers is even, then both numbers are even. If the sum of two numbers is even, then both numbers are even. Now I could write a biconditional, but I want to write a true biconditional, which means both directions are true. We know the first way is true. If the sum of two numbers is even, every single time are both numbers even? No, right? That doesn't work. Now, so we could say, okay, no, that's false. That doesn't work. If it's false, you should be able to give me a counterexample. What? 3 plus 3. Both odd, right? That gives me 6, an even sum, but 3 and 3 are odd. Good. Good. Okay, questions on writing those biconditionals? Okay, let's go the opposite way. Let's look at a biconditional and see if we can write out the two statements from each direction. So number 3 says, two numbers are additive inverses if and only if their sum is 0. Two numbers are additive inverses if and only if their sum is 0. Okay, now if I want to write the two statements are going to be conditional statements. So these statements need to be in if-then format. Okay? So what's the first statement I could draw from this? What's one of them? Do what? Now, like I'm talking like an if, da-da-da-da, then da-da-da-da-da. So using both pieces of information. Oh, an additive inverse is like 3 plus negative 3. 5 plus negative 5. 10 plus negative 10. So additive and then inverses would be 10 and negative 10. So what would be one direction here? Start with if. That'd be a good place to start. If two numbers are additive inverses, then their sum is 0. Yeah. Just kind of got to take the biconditional, throw the if in front, the then in the middle. May have to rearrange the words a little bit, make sure it makes sense. Now, once you come up with that one, to come up with the second one, you just kind of do the converse of that. What would be the converse of what we just wrote. You're mumbling, but I think I got the right idea. If the sum of two numbers is 0, then they are additive inverses. If the sum of two numbers is 0, then they are additive inverses. Okay, so next we're going to kind of come into this idea of a good definition. The biggest thing we're going to run into when it comes to definitions is they're going to have to be reversible. Most of the time, definitions have common, easy to understand words. Most of the time they're precise, but they have to be reversible. Okay, meaning you could read them both directions and they would be true in both directions. So that's what we're going to look at. We're going to decide if it's reversible. And if it is reversible, we're going to write it as a true biconditional. Okay? So number 4, an equilateral triangle is a triangle with 3 congruent sides. And I'm okay if you guys want to use the notation of the congruent symbol instead of writing it out. An equilateral triangle is a triangle with 3 congruent sides. Now, this isn't a conditional, it's just a statement. So when we're checking to see if it's reversible, you could write it as a conditional if you wanted to. Don't have to. We could just reverse it. So instead of starting with the equilateral triangle part, the second part is the 3 congruent sides. So let's say, okay, a triangle that has 3 congruent sides is an equilateral triangle. A triangle that has 3 congruent sides is an equilateral triangle. So I know it's not a conditional, but is this true? A triangle that has 3 congruent sides is an equilateral triangle. I'm not familiar with that word. Equilateral. Equilateral is sides. It means equal sides. So an equilateral sides, yeah, it's going to have 3 congruent sides, okay? So we could write this as a true biconditional, okay? Remember, a biconditional doesn't have the if-then, okay? So this one, you're really just going to take this and you're going to plug in if and only if right there. So maybe rearrange the words a little bit. So you kind of have to think ahead a little bit. So we're going to say a triangle is an equilateral triangle if and only if it has 3 congruent sides. A triangle is an equilateral triangle if and only if it has 3 congruent sides. Okay, let's do one more of those. Okay, number 5. A straight angle is an angle that measures 180 degrees. A straight angle is an angle that measures 180 degrees. Okay, so first thing, if I wanted to reverse this, if I'm going to give it a shot, what would this look like if I reversed it? Yeah, an An angle that measures 180 degrees is a straight angle. Well, an angle that measures 180 degrees, think about what that would look like. Is that a straight angle? Yes. So I could write this as a true biconditional. I'm going to give that a shot. I would take that statement and maybe rephrase the words a little bit. Plug if and only if.
An angle is a straight angle from if only if.
Yeah. The first part is the part that you kind of got to talk through. So you might say, an angle is a straight angle. An angle is a straight angle. Gotta have the if and only if it measures 180 degrees. Yeah, good. Okay, so we practiced reversing a statement. That's going to be the biggest thing, maybe I guess the hardest thing to check whenever we're talking about this idea of a good definition. So we're going to do two of these. I'm going to throw a couple of definitions up here. We're going to decide if it's a good definition. Remember, if it's a good definition, it needs to use commonly known words, it needs to be precise, and it needs to be reversible. So number 6, a dog is an animal with 4 paws. A dog is an animal with 4 paws. Okay, first thing, uses clearly understood words. Dog, animal, paws. Okay, precise. It didn't say a dog is an animal with a few paws. Right? No, it says a dog is an animal with 4 paws. Okay? Reversible. If I reverse this, what would it say? An animal with 4 paws is a dog. Now remember, it would have to be true every single time the hypothesis is true. The conclusion also has to be true. So every animal with 4 paws is a dog. No, right? No, we got cats and horses and horses don't have paws today. Anyway, bears, whatever. Okay, so we say no, and your explanation, not reversible. It is not reversible. And last one. A penny is a coin worth 1 cent. A penny is a coin worth 1 cent. Okay, clearly understood terms. Yeah. Precise. Doesn't say penny is a coin that's worth some money. Okay, no. So it's precise, worth 1 cent. Reversible. What would this read if I reversed it? A coin worth 1 cent is a penny. Now, is every coin that's worth 1 cent a penny? Yeah. So, yeah. So it is a good definition. So we'll say yes, and we could say it is reversible.